Hello class. Today we're going to continue our discussion of equations with variables on both sides. Equations that look like this right here. And we've learned that there are basically 3 steps to solve a problem like this. Step number 1, get your letters on one side. How do I do that? Add the opposite. Get the numbers on the other side is step number 2. And how do I do that? I add the opposite. And then last but not least, solve. And how do we do that? We do the opposite, or we do an inverse. Now sometimes our equations are going to have pre-steps though. In this particular one, there is a pre-step that we need to do, or that I like to do. We don't have to do it, but I like to do it because it prevents careless mistakes. So I see that there's a minus right here, so I'm going to change the subtraction to addition and next to its opposite before I actually work it. So now we're ready to begin step number 1. Get the letters on one side. Most of the time we like the letters to be on the left. So we start at the equal sign, and I'm going to move the 7x to be with the 4x. So we do 7x plus negative 7x plus 13. So the negative 7x is the new thing that I need to put on the other side. So then 4x plus negative 8 plus the new thing that I added on the other side, which is the negative 7x. Now we can combine like terms. The negative 7 and the 4 go together to make a negative 3x plus negative 8, which is equal to, my 7x's go away, equal to 13. Now we just need the negative 8 to be moved to the other side. So negative 3x plus negative 8 plus 8 equals 13 plus 8. Our 8's go away on the left, so I'm left with negative 3x is equal to 21. Now, we divide both sides by negative 3, and we end up with x is equal to negative 7. One of the big things that I've seen happening right now in class is that when we have a divide by or a multiply by negative 3 or a divide by negative 3, we need to remember that the number I multiply or divide by has to be the same number when we're solving. If it's not the same number, I'm not going to get a positive x. Now, why are we working on this so hard? Well, the state of Texas says that we need to solve one variable equations with variables on both sides of the equal sign. So that's the reason why we're pushing so hard. The state of Texas feels this is important, and so do I. You cannot be successful in Algebra 1 next year if we can't do this. So now, today I'm going to stretch your brain a little bit. We're going to do several stretches of this particular thing. We need to look at some special circumstances. And here's our first problem. You'll notice that this one is a little bit different. That this one's got a 4x plus 6 on one side, but I only have an x on the right. Okay, so what I need for you to think of on this one when I'm going through those steps, step 1, get the letters on one side. Step 2, get the numbers on the other side. Are one of those already done? Now, if you'll notice, I do have letters on both sides, but I only have a number on one side. So my numbers are already together. One of those first 2 steps is already done. So now what's really difficult is we've been moving our variables to the left-hand side. In this particular problem, it's better to move your variables to the right-hand side. And the reason why is because my numbers are already together on the left. So on this one, I'm going to move the 4x over to the right-hand side to be with the x. So 4x plus negative 4x plus 6, so here's the new thing, equals x plus negative 4x, and I added it to both sides. So now my x's go away on the left, and I'm left with 6, which is equal to, and then we need to remember that this x that's by itself does have a 1 in front of it. We just don't write that. So 1x plus negative 4x gives me negative 3x. Then I divide by negative 3, and I end up with x is equal to negative 2. Okay, so sometimes we have to look at our problem and see, is there anything done for us already? Okay, and then go forth from there. Now, that's the first stretch, okay, moving the letter to the side we don't really like. Now let's look at the second stretch. So here's our second problem. But this one looks like a normal problem. I have letters on both sides, I have numbers on both sides. So solve this the way I've been teaching you. Step number 1, get your letters together on one side. So I'm going to move the 9w over to be with a 9w. So equals 9w plus negative 9w plus 7. So there's my new thing. So then 9w plus 3 plus negative 9w. So now I put things together. Now hopefully you see something happening here. this 9w and this negative 9w, they actually cancel each other out. They eliminate each other. Okay, so all I'm left with on this side is just 3. But on the right-hand side, again, I have the 9w and I have a negative 9w. Again, they eliminate each other and we only have 7 left. Okay, so when we have a problem like this, whenever my variables are eliminated, and this makes a false statement, 3 does not equal 7, here's what we do. We say that 1, it's not equal, and 2, there is no solution to this problem. So no solution, and that's what we write. We cross out the equal sign saying that it's not equal, and we write no solution. Because what that means is that there's not a value that I can plug into this w. There's not a real number that I can plug in that will work. So again, if the variables in an equation are eliminated, they go away, and the resulting statement is false, the equation has no solution. So you have to be able to recognize when my variables are going to cancel out and whether or not that's going to make a true statement or not. So let's take, for example, let's look at this one. Okay, I'm hoping that you see that, okay, I've got a 3w here, I have a 3w here. So my 3w's are going to cancel each other out. So 3w plus negative 3w plus 8 is equal to 3w plus 1 plus negative 3w. My variables are going to cancel out, and I'm left with 1 equals 8. Is that a true statement? No, it's not. So it's not equal, and we say no solution. So if the variables are eliminated and it's a false statement, it's no solution. Let's look at one more. So in this particular problem, you'll notice that it looks like there might be some pre-work that we need to do. Okay, pre-work would be either change minuses to plus next to their opposites, or look for anything that can actually go together. And in this case, the 3 and the 4 could go together. And I'd end up with 5m plus 7 is equal to 5m plus 7. That's interesting. Well, let's go ahead and solve this one just like we did the previous ones. So I'm going to move this 5m over on to the left side. So 5m plus negative 5m plus 7. And then 5m plus 7 plus negative 5m. Well, again, our variables are eliminated on both sides. So I end up with 7 is equal to 7. Now this one's a little different from the previous problem we just worked because our ending statement, our final statement, that's a true statement. So 7 is equal to 7. Okay, so if my variables are eliminated and it makes a false statement, then it's no solution. But if it makes a true statement, then we say all real numbers. Because any real number that I plug into this m will be a true statement. Now let's redefine, let's kind of remember, what is real numbers again? And real numbers are any number that can be put on a number line. It is a combination of both rational and irrational numbers. Now, in the real world, if anybody ever comes up to you and yells out an equation and says, hey, what's the value of m? Just turn around and run, because that's not going to happen in the real world. In the real world, everything comes to us in a word problem. And what you're going to have to do in a word problem situation is pull out what I need in order to do the math and then solve. So in this particular problem, it says Daisy's Flowers sell a rose bouquet for $39.95 plus $2.95 for every rose. A competing florist sells a similar bouquet for $26 plus $4.50 for every rose. Find the number of roses that would make both florist bouquets cost the same price. Okay, so in this particular one, we've got two flower shops. Daisy's Flowers sells a bouquet of flowers for $39.95 plus $2 per rose. Okay, well, I can actually write that in algebra terms as an expression. $39.95 plus $2.95 for every rose. And that is our variable, rose. And I like to use variables that mean something into the problem. Okay, a competing florist sells a similar bouquet for $26 plus $4.50 for every rose. And it says, find the number of roses that would make both florist bouquets cost the same price. So I'm trying to find out where these two are equal to each other. So we set up an equation, and this time with variables on both sides, and we solve it. Okay? And there are several things that we do with these, whenever you are looking at these kind of problems. So, as we work through them, in class, I need you really paying attention to how the expressions come together. Now, there'll be another lesson that actually has some more explanation on the real-world application of this. So until next time.